Welcome to Lesson 2.2, Day 2. The learning targets today are that you should be able to state and identify the way the graph will look using the multiplicity of a zero, and that you should be able to write or build polynomial functions from the zeros, including considering multiplicity if you're giving a sketch of a graph. So you are going to start by looking at this exploration. And I'd like you to quickly graph the two on your calculator, identify the leading term and whether it's positive lead coefficient or negative, and the degree, and do a quick sketch of the graph, identifying the x-intercepts, either from solving algebraically. It does say find them by factoring, and you can even check them on the graph. All right, welcome back. So hopefully you have factored out x squared, and you had x squared plus 5x plus 6, and you had x squared and then x plus 3 and x plus 2 by factoring. This should have given you x-intercepts of x equals 0, x equals negative 3, and x equals negative 2. So on our graph, we would have one at negative 3, one at negative 2, and one at 0. Our leading term is x to the fourth, which is positive. So we have a positive lead coefficient of degree 4, so we expect the graph, at least in terms of the end behavior, to open up. And so when I go to sketch this graph, I'm going to come up off of this one and also come up off of this one. And then the question is, what happens in between? So you're going to graph this in your graphing calculator to see what happens in between. We have x to the fourth plus 5x cubed plus 6x squared. And what happens when we do our standard zoom is we can see that it comes below the x-axis a little bit, comes back up and intersects this, and it looks like right over here it touches at 0, 0 and bounces back up. It doesn't actually intersect or cross over the x-axis. So at these two it intersects, which means that it crosses over. This intersects the x-axis, and here it touches and bounces back. In our next function, if you factored this correctly, by the way, the leading term was x to the fourth, so we know it had a positive lead coefficient and degree 4. So with that even degree and positive, we expect the end behavior to be opening up on both sides of this function. The zeros were 0 and 2, which are obtained from the factors. On this one, if you look at the graph of it, it touches at those spots. So here's 1, 2, 1, 2. We have an x-intercept of 0, an x-intercept of 2. It touches and bounces back. So we have it opening up on the left and opening up on the right. And then it touches and bounces back up and comes down and touches and bounces back up. So on both of these, it touched the x-axis and bounced back above the x-axis. Graphing the polynomial function, we're looking at these. These ones are already factored for us, so we know this x-intercept is x equals 0. If I set 3x plus 1 equal to 0, I can subtract 1. 3x is negative 1 divided by 3. X equals negative 1/3. On the other one, I have x equals 2. Plotting those points, so here's negative 1, negative 2, negative 3, 1, 2, 3. I have 0, I have 2, 0, I have 0, 0, and I have negative 1/3, 0. Probably should have scaled it a little different to make it go out more. Well, if it follows the same behavior as last time, as the other ones, it's probably going to cross here, and probably bounce here, given that extra factor of x minus 2. So we're going to look on the graphing calculator with that. We have y equals x by 3x plus 1 by x minus 2. And when we do this on the graphing calculator and look at the graph, Sure enough, by the way, this is a fifth degree polynomial, x squared, 3x cubed, x to the fifth, 3x to the fifth. So we expect it to act like an odd degree polynomial with a positive lead coefficient, the end behavior to be like a graph of a line with a positive slope. So from here, this one shoots down. From here, this one shoots up. What's interesting is that was x equals 2 and it was squared. Did I not put it in the calculator right? I did not put it in the calculator right. This is not a fifth degree polynomial. That's 2, 3, 4. It's a fourth degree polynomial. So we expect both ends to open up just like above. And in fact, we can see that it comes down. Let me do this in purple so you can see the actual graph. It comes, there's our sketch of the graph. It comes down and intersects this x-axis and comes back up and intersects this x-axis. And then it comes down and bounces back up. So what I have in black over here is inaccurate. I didn't put it in the calculator correctly. So again, we get a bounce here, and we get intercepts or intersects the x-axis. All right. And in the same next two graphs, we're going to see something very similar, but it's a little bit different. So pause the video and so you can get a sketch of those graphs real quick. All right, for both of these functions, I looked at what the lead coefficient would be by expanding. That's x cubed, 2x to the fourth, 2x to the fifth. This is x cubed, x to the fifth, 3x to the sixth. They're both positive. This one's going, its end behavior is going to function like a line because of the odd degree. This one's going to function like a parabola in terms of the end behavior because of the even degree, and both are positive, so that's what we expect the end behavior to do. Our zeros based on these factors are 0, 3 halves, and -1 for the top one, 0, -2, and 1 for the bottom one. What's interesting is when I look at the graphs of these. I have x by 2x minus 3 by x plus 4. And this one is cubed. And when I look at the graph of this, sure enough, just as I expected, this goes down. But then it shoots up from here. And again, I don't think I put this in the calculator right. It just does not look right to me, but it's showing that it is. Zoom. I'm actually going to change my window to see if this makes any difference. Probably not. Oh, it does. I can see that it's going up. Then it comes back down across 0. I couldn't see it because it was so close to the x-axis, and then it comes back up. And notice this little twist in the graph here comes up, and at that point it kind of does this twist. So it was going down like this, and now it's suddenly going up like this, and it does a little maximum up here that's not on our graphing calculator that we can't see as well, so we're not zoomed out enough. And then it comes down very sharply, and then x plus 2, I don't know. Oh, I'm in the wrong graph. I'm supposed to be doing this one. It does this twist, comes up very sharply, comes down, and then comes back up. So there's our fifth degree polynomial. Those are the zeros. At all of them, it intersects at all. But at this one in particular, why do I have -1? That should be -4. Yikes, no wonder. At that one in particular, it has this little twist in the graph. So it intersects and twists for this one. For the next one, I started sketching it, and it looks terrible. But it's x to the 6th, so I'm expecting the end behavior to go up. So I'm going to just go in and change my factors real quick. I've got 3x by x plus 2 quantity squared by x minus 1 quantity cubed. When I hit the graph, and I want to go back to my standard mode, although it's working, zoom standard, I could see the end behavior at least. And I actually want to go in a little bit, so my x minimum is maybe -6. My x max is maybe 6. This might give us a better view of what's happening in there. Not much. A little bit. It is shooting up off of this, so ignore the black. No, not that one. This one, coming up off of this. It does bounce there, kind of like I would expect, because it did that on the other page. So there's a bounce there. Then it comes up and bends back down and crosses this axis. And then it does this funny little thing where it kind of does this little twisty behavior over here. You can see that on this graph. It kind of comes up and right there does a twist. It was coming up here and it kind of twists at that point. So that's at 1. So that's our twist. And here it just intersects. Here it twists and intersects. So if you read below, it talks about multiplicity. This is directly out of your book. But what you should see or be able to conclude from this is that when we have multiplicity, a factor that is in the equation more than once, if m is even, like we had here with the squared or on the other page, if we have two factors leading to the same x-intercept, the graph is going to bounce. It's going to touch and bounce at the x-axis. That's actually technically called a point of tangency. It's going to be tangent to the x-axis. It's a point of tangency there. When it comes down and touches and bounces back. That wasn't part of our graph. If it's just a regular factor, it just intersects as always. But if m is odd, then it does something else that's unique. It intersects and it does a twist. A little odd twist. So if it was kind of curving this way, as soon as it hits that 0, all of a sudden the curve it's more concave that way. So it was concave to the right, now it's concave to the left as it hits that 0, if there's multiplicity. And you can even see that on the function y equals x cubed. You see the graph come up, it touches the x-axis, touches and crosses over the x-axis and twists, so it's concave to the right and then concave to the left above the x-axis. And it could be concave the other way as well, but that's what's going to happen when we see a twist. So now, instead of using the graphing calculator and doing this little exploration thing, we're actually given these functions and we are asked to apply the leading terms test. The leading terms test is going to tell us what's going to happen to the end behavior, determine the zeros and state the multiplicity of any repeated zeros, and then sketch a graph. So the leading terms test, x squared, 3x cubed, 3x to the 4th. Since it's both positive and even, we know the end behavior of this particular function is going to be like a parabola when we go to sketch our graph. Determine the zeros. Well, lucky for us, it's already in factored form. So my zeros are x equals 0, x equals -1/3, and x equals 2. The x equals 2 has multiplicity of 2. So when I graph this, I'm expecting a point of tangency or a bounce. So I'm going to quickly sketch a graph without my calculator, and I can always put it in to check it. But I have at 0, I have an intersection point. At 2, I have an intersection point. And here's -1, -2. So right here would be -1/3. We know it's even, so we know the end behavior after it leaves this point is that it opens up. And after it leaves this point is that it opens up. We also know that it's going to intersect at -1/3. And then it comes back up to intersect at 0. And then because of the multiplicity of 2, it comes down and touches 2 and bounces back up. So what I see in blue is my sketch of the graph based just on the leading terms test and the zeros, including keeping reference to the multiplicity. In the next problem, we have x cubed, 2x to the 4th, 2x to the 5th. So it is both positive and odd. So we expect the end behavior to function like a line with a positive slope. If it does this, we also have x equals 0, x equals +3/2, and x equals -4. But the x equals -4 has a multiplicity of 3. And so at that particular location, I'm anticipating an intersection that crosses over the x-axis with a twist. So I'm going to do a quick sketch of this. I have negative 1, 2, 3, 4, and I have 0, and I have 1, 2, and in between is 1.5 or 3 halves. We already know the end behavior from the leading terms test. This one's going to shoot down. This one's going to shoot up. At negative 4, though, we expect a twist. So this one shot down being concave in to the right. And as it comes off of that, it's actually going to be concave to the left, or maybe it'll be the reverse of that. At 3 halves, it's going to, at 0 and 3 halves, it's going to intersect. So it's going to eventually come down and intersect the x-axis, and then come back up and intersect the x-axis. Pause the video for a moment and try the next problem. If you did this problem correctly, using the leading terms test, you had x cubed x to the 5th, 3x to the 6th. Positive lead coefficient, even degree means they're going to, the ends are going to function like a parabola with a positive lead coefficient opening up. The zeros are 0, negative 2, and positive 1. And positive 1 has a multiplicity of 3, giving us a twist. And negative 2 has a multiplicity of 2, so we're expecting a bounce. So when we go to graph this, we're going to draw our x-axis. We have to make sure we have 0 and negative 2 and positive 1. We know that at negative 2 there's a bounce, so it is going to come up as it goes to the left based on our end behavior. We know 1 is going to have a twist, so it's also going to come up. I'm going to intentionally draw it concave to the left. Because of the twist, when I come down, I'm going to go concave to the right. Then I'll have a turning point in here. It does intersect at 0, so this one's going to come back up and intersect at 0. This was supposed to be a bounce, so it's going to bounce back up, and that's going to meet right there. So that's a quick sketch of the graph. We could plug it in the calculator to verify, but we need to be able to justify our graph, showing the zeros on our graph, stating the multiplicity and what's going to happen at them, stating the leading terms test and how that affects the end behavior and what we expect to see on the graph. This concludes the learning target for being able to sketch graphs and having identified multiplicity and being able to describe how the multiplicity will affect the graph. The last learning target of lesson 2.2 is for you to be able to build a polynomial function. So you're going to check this with your graphing calculator when you're done. But what we have here is that ax minus b is a 0 if and only if x equals b over a. Let's think about that for a second. I have x equals some fraction, some rational number. If I were going to get this equal to 0 so that it looked like a factor, ax minus b equals 0, I would have to multiply both sides by a and then subtract b to get it equal to 0. Now we don't normally do this. Normally we work in reverse. We start with a polynomial function written in standard form, not in factored form. We factor it, we get the factors, we set them equal to 0, and we solve them to get our answers for the x-intercept, or zeros, or roots. In this case, we're going to be given the x-intercepts, and we're going to write them like this, and we're going to work backwards to figure out what the factors were, and then we're going to distribute to simplify and build those equations. So on this first one, we have these 4 roots, or 4 zeros. And I'm going to just write them, even though I know that one has multiplicity, I'm going to just write them as x equals 1, x equals 1, x equals negative 4, and x equals positive 7. To make them look like factors, I either need to subtract or add to get them equal to 0. So here I'd have x minus 1 equals 0, x minus 1 equals 0, and here x plus 4 equals 0, and here x minus 7 equals 0. Now that it's in factored form, I can do the reverse of factoring, which is distributing or multiplying to get the answer for that. So I have x times x, which is x squared, minus x, minus x plus 1. That's x squared minus 2x plus 1 for just the two factors multiplied together. For these factors multiplied together, I have x squared minus 7x plus 4x minus 28, which is going to give me x squared minus 3x minus 28. I'm now going to distribute these. So I start with my first term, x squared. That's going to give me x to the fourth minus 3x cubed minus 28x squared. Now I'm going to distribute the negative 2x. That's going to give me negative 2x cubed positive 6x squared and positive 56x. Now I'm going to distribute the positive 1. X squared, negative 3x, negative 28. And now I'm going to add vertically. So I have x to the fourth minus 5x cubed. That'd be negative 22 plus 1, which is negative 21x squared, and that would be negative or positive 53x minus 28. Here is a polynomial function. Maybe it has a multiplier on it of a number. I'm not sure. But I know that this is my one of the polynomial functions that would have these as the zeros. I can even put this in my graphing calculator to check my answers. So I can do x to the fourth minus 5x cubed minus 21x squared plus 53x minus 23. When I go to my table, if I plug in 1, that's a problem. Hold on, x squared minus 5x to the third minus 21 plus 53 minus, not minus 23, minus 28. I wrote it wrong. So this should be minus 28. So when I plug in 1, I should get 0, and I do. And when I plug in negative 4 and 7, I should also get 0. And I do for all of them. So I know it worked because those are the zeros, and they give me 0 when I plug them in. Now another way, if you didn't like distributing those by distribution, you can use a method called box method or table method. I normally don't prefer to do this way, but it is something we can do if we need to. So we could always do x squared minus 2x plus 1 and x squared minus 3x minus 28 as a multiplication table if we needed. This product being x to the fourth, this product being negative 28, and so on and so forth with all the terms in here. Negative 3x cubed, negative 28x squared, negative 2x to the third, positive 6x squared, negative 56x, x squared, and minus 3x. And then we just add them this way for combining our like terms. We'll get the exact same function. So if you don't like distributing when there are more than two terms, you could use this to help you. On this next one, our factors are our zeros are x equals 1/2, x equals 3, and x equals negative 6. So when I do this, I'm going to multiply by 2 first, and then I'm going to subtract 1. 2x equals 1, then I subtract, so 2x minus 1 is the 1 factor. On this one I have x minus 3, and on this one I have x plus 6. So all I need now to distribute these three factors, since there were 3 zeros, I expect a cubic equation. I'm going to distribute these two first. That's going to give me x squared plus 6x minus 3x minus 18. So x squared plus 3x minus 18. To that I have the 2x minus 1. I can distribute the 2x first, giving me 2x cubed plus 6x squared minus 36x. Then I can distribute the negative 1 minus x squared minus 3x plus 18, giving me 2x squared plus 2x cubed plus 5x squared minus 39x plus 18. And when I put that into my calculator, 2x cubed plus 5x squared minus 39x plus 18, and go to the table. If I put in 1/2, 3, and -6, I get 0 for all of those, so I know I did it correctly. Now you're going to follow the same process we just did for these if you have graphs instead of just being given the zeros. Eventually we'll be doing this with irrational roots or irrational x-intercepts, not x-intercepts, and irrational x-intercepts and complex solutions as well. But right now we're doing this with only real zeros. So when I look at this, that just intersects, that just intersects, that just intersects. So I have x equals -3, x equals -1, and x equals 2. I don't see any twists at those intersections. I don't see any multiplicity from twists. I don't see any multiplicity from bouncing. There is no bouncing in this one. So I would just set up my factors, x plus 3 by x plus 1 by x minus 2, and do as we did above to distribute those, or FOIL them if you want, to get your solution in standard form. I'm not going to do that right now, I'm just showing you how to get them from the graph. Now this next example is a little trickier. We do expect an even degree polynomial because it's opening down. By the way, on this one, this is functioning like a line, like an odd degree polynomial, an x cubed, which we'll get, with positive n behavior, so a positive lead coefficient. So when I multiply those, I get positive x cubed, I'm good. This one, however, its n behavior is opening down, which means it's even degree and has a negative lead coefficient. I have to keep that in mind at the end. This root is x equals -1, but it bounces. So I'm expecting even multiplicity, and the minimum even I could have would be 2 factors there. And then this one intersects, and this one intersects without any twisting. So I'm expecting just regular x equals 2 and x equals 3. That would give me 1, 2, 3, 4, which would be an even degree polynomial. And then I'm going to build my factors. So my factors for this one will be x plus 1 by x minus 2 by x minus 3. The x plus 1 had even multiplicity, though, as indicated by the bounce, so I'll put an exponent of 2 on it. This also gets us a 4th degree polynomial. Now, because of the negative n behavior, we're going to have to put a negative sign in front of all of this. And so if or when I go to distribute this, I would distribute all those terms, and then the very last thing I would do once I have it in standard form is distribute a negative sign to every single term in that quartic equation. Take a moment to identify what the zeros are and whether you think there are twists or what you think the multiplicity should be for those. Here we have a 0 at x equals -5, and it's a bounce. So I'm going to put multiplicity of 2, but I know that it could have more than that. So I'm going to say that that's a minimum multiplicity of 2. I have an x-intercept at x equals -1. It doesn't look like it twists there necessarily, so I'm just going to leave that as a regular x-intercept. There is this weird thing happening where the graph, where it's concave to the right and then concave to the left at 4. So I'm going to say that that one has an odd multiplicity, and the minimum for an odd multiplicity is multiplicity of 3. And then at this x-intercept, it just kind of doesn't do any twisting or anything, so x equals 7. So that means I have x plus 5 as one of my factors squared. I'd have to expand and distribute that, or FOIL it. I have x plus 1 as one of my factors. I have x minus 4 as one of my factors with an exponent of 3. And I have x minus 7. This adds up to a 2, 3, 4, 5, 6, 7th degree polynomial, x to the 7th. It's an odd degree polynomial, and when I look at the n behavior, like a line, it's more like a line with a negative slope. So that means it's got to have a negative lead coefficient. So after I do all of that expanding, I'd have to distribute a negative into every single term. And for our last one, this is x equals -5. There's no twists or turns or bouncing there. This one maybe it kind of looks like it's concave this way and then concave that way. So it is possible to have multiplicity at that one, -3, and it would be odd multiplicity because it's a twist. At x equals 0, apparently I have the same thing, concave this way and then concave that way. So x equals 0 will also have multiplicity of 3. And then at x equals 2, yeah, it was concave this way, but then it kind of just goes straight down. There's not really a turn in it. So until later. So I'm going to just say that that's a plain old x equals 3. Let me see if this is going to give us the right thing for odd degree. There's 6, 7, 8. No, that would give us even degree. So either one of these is not. That looks like it twists there. Maybe it does actually twist here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I didn't put the last one on there. That's why. X equals 5. So that is an odd degree polynomial. 6, 7, 8, 9. It's an x to the 9th. And its end behavior is functioning like a slope of a positive line. So I don't have to worry about a negative symbol in front of everything. I'm going to build my factors down here. I'll do that in red. So I have x plus 5, which is a single factor. It's just an intersection point. X plus 3 cubed, x cubed, x minus 3, and x minus 5. If I were doing this, I would probably start by expanding these two, expanding this, and then multiplying it by this, and then distributing the x cubed into everything. But there's our 1, 2, 3, 4, 5, 6, 7, 8, 9 factors giving us our x to the 9th equation. And so I would expand those factors. We have reached the end of lesson 2.2. At this point, you should be able to say that you understand how to describe the multiplicity of a 0, and that you could sketch a graph from that. Also that you could write or build a polynomial function from zeros, whether they be given to you as x-intercepts or zeros, or whether they be given to you on a graph. Hopefully you can answer yes at this point. The assignment that goes with this section is listed below. It is also on your assignment guide. One of these is listed twice. We're not doing 69 to 74. It says all actually on our sheet. I'm okay with you doing odd for today. That's fine. Try to get those done in class as much as you can. Whatever you don't finish in class, you do for homework. Please compare answers with the people at your group table while you're working to make sure you're doing it correctly. Have a great day.